By popular request, I'm going to open up the lab tomorrow morning from 10 to 12:30. So it'll be Tuesday, 10 to 12:30. We have to get out of there. It might be till 1, but I'm not sure yet. And then Wednesday, we can't be in there in the afternoon tomorrow because 2300 thinks they have time in there too. Then on Wednesday, of course, we'll be open from the usual 10 to noon. Will you be there, Pavel? Yeah, I will be too. And then the rest of the week's schedule should be the same. Sorry I had to miss the end of last week. My wife had some surgery. It went well. I'm sort of on reduced hours this week, so I won't be around in the mornings a lot. I'll be around in the afternoons. Any questions about Lab 3? It's going okay? You're not sure yet? Haven't started yet? I hope it, it's going badly. 1, 2. Yes, okay, yeah.
So how many voices do you need for 2 credits? Because it said that points are reserved for having extra voices.
Well, so I understand that students like to have a criterion, and I could do the mean thing and say I'll rank order them, but that means that everybody has to work as hard as possible until the last possible minute. So I'm not going to do that on this lab. I did it on the final project. But I would say if I scaled it right off my code, it should be possible to do 5 or 6 voices at 8 kilohertz. Yeah, and therefore 2 or 3 at 16 kilohertz, which makes more sense than trying to go for a god-awful number of voices. I expect there'll be somebody who will figure out some twisted method to get 25 voices.
We were thinking about overclocking the board with a different crystal.
Sure, why not? Go for it. Watch the smoke come off. The overclocked. I think you can overclock 20%, but not much more than that, unless you go to Freon cooling. Yeah. Yeah.
We had a question about what you meant in the assignment by 4 changeable parameters.
4 changeable parameters. So each voice is defined by about 6 parameters, right? There's the base frequency. You can't change that because that sets the pitch. There's the FM modulation frequency, which you could change. There is the FM depth, the rise main envelope rise time, the main envelope fall time, and the FM decay time. I think that's 6 parameters. 4 of those have to be settable.
Settable meaning when you press different buttons?
Yeah, yes, the human settable. Not reprogrammable in the sense that you open up the code and recompile and reload it, right? It's got to have a user interface. So it's playing along, going ding, 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 ding. You press some buttons and it goes bong, 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 bong. Or crash, 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 crash.
So the user doesn't choose like value. It's just
The user chooses values.
Oh.
You get to restrict the values to something reasonable. Like I think that FM depth is an integer and should be probably constrained to be between, say, 4 and 12. Hit a button. Is it okay to hit a button and cycle through, or do you actually have to input a number? I'm going to leave that up to you as long as it's usable in a reasonable fashion, where reasonable is defined by the TA. You have reasonable TAs.
Yeah, a lot of people ask that question, and pretty much what I said is that it's fine depending on what synthesis you use. For FM it works because all those 4 parameters are integers. But if you do KSA, for example, and you need to enter 0.01, then you probably need to enter string.
Very good point. Right. If you're using FM synthesis, it's mostly you can get away with only entering integers, unless you want to enter the single-digit integers, unless you want to enter the FM frequency, and that would probably require 3 digits or 4 digits. If you're going to do KSA or even synthesis, additive synthesis, you'll probably have to be able to input arbitrary strings.
Is there a requirement to be able to change the synthesis parameters during like the...
Sure, you should be able to have it play and just change the parameters. Don't have to have it stop.
We have preset sort of possible voices, so rather than entering parameters one at a time, you can choose a kind of voice like a chime or a bell or a string. Would that still work, or do you want the leave
All right, so that's kind of changing the requirement in a way which is still interesting, right? It's not like you're trying to get out of work here.
Yeah.
It's like you're changing the assignment. And in some ways that makes more sense, but you don't have as fine a control that way, right? Because you're going to choose 5 or 8 or 25 voices. Whereas if you allowed the person to choose all possibilities of 4 parameters, you have something like 6 to the 4th possible voices. So I guess my inclination is that you should stick with the specification on this one. You could have a mode where you pick instruments instead of parameters, but you should be able to pick individual parameters also. For additive synthesis, how many terms per voice? It's up to you. And you're going to be, so as I said before, there's a sort of the time-consuming piece of this is the per sine wave rising phase, falling phase, and direct digital synthesis calculation. And so for extra point grading here, for speed grading, we're going to say number of amplitude modulated direct digital synthesis units that you're using. All right? So I would say minimum of 3, because unless you get to the 3rd harmonic, you can't capture anything like a square wave or a triangle wave, and or a sawtooth. And probably 5 is better. Above 5, it's going to be subtle. Between 3 and 5, you'll notice a difference, certainly.
I think it's important to turn off the number of voices and terms per voice. So should we still be targeting 6 voices and still targeting 5 terms?
You can't possibly do that. It's the number of total DDS, amplitude modulated DDS units. So for an FM voice, you have 1 amplitude modulated direct digital synthesis plus 1 for the FM modulation. So that's 2 FM modulated, 2 amplitude modulated DDS units. For direct digital synthesis with 3 sine waves, you have 3. So we're going to do something like the number of DDS units. But if you're going crazy with number of voices, it's going to make a lot more sense. It's going to be easier to listen to, easier to grade, it's important, and easier to understand if you just jack up the sample rate. Right? Because it's the product of sample rate and number of voices that matters. Anything else?
So I found that when I changed any of the parameters to the LCD, the rate, like there's a pause in between the notes.
Well, because the LCD takes so long to write.
So that's okay.
No. The longest operation on the LCD is LCD clear. Do you do an LCD clear every time you write it?
No.
Good. Don't do that. You can't do that. But if you only change 1 or 2 digits, it'll be pretty fast. It'll be a millisecond per character. So you may have to optimize that. You may have to not do an LCD update on every operation, but just a couple of times a second, or between notes, at the break between notes. If you're playing 4 notes a second.
Is the LCD light operation, is that blocking on the interrupt?
It is not blocking on the interrupt, but it is blocking on the date on the calculation of the Markov string.
Oh, okay.
Now, as far as I know, there's no blocking code in the LCD library. If, however, you go to very heavy CPU loading, because after all, you're trying to do heavy CPU loading here, you will find that the LCD library will be very slow because it uses software timing loops, which get clobbered by interrupts. Another question? So lab 3 is well defined. Yes. Yeah, one type of wave. That's another parameter you could choose, is to say, instead of having a sine wave in my direct digital synthesis table, I'm going to use a sawtooth or a triangle wave. That's yet another parameter, but no, you don't have to do that. What? That is a parameter you could adjust, is sine wave versus sawtooth versus triangle wave. Percentage, oh, asymmetry, ooh. Make it, so you have an adjustable asymmetry from 50% duty cycle to 95% duty cycle. Yeah, that'd be fun. Lab 4. Let's talk about Lab 4. So the overview of Lab 4 is that you're going to build a tachometer motor controller. So you're going to measure the speed, a rotation of a fan, and then you're going to control that speed. So the user will be able to type on putty. Now this is going to be serial control. The model for this is kind of like remote control of an industrial process. So the user will be able to type on putty RPM equals 1,000, and the motor should speed up to 1,000 RPM. Or should be able to set RPM equals 500, and it should slow down to 500 RPM. Furthermore, it should do that without excessive fluctuation or overshoot. In other words, I want a fairly optimal control system. If you command the RPM to jump from 500 to 1,000, then the motor should come up to speed fairly smoothly and fairly quickly. We'll define what that means later. And not do this. So it should not overshoot too much. It should not oscillate for a long period of time. It should be fairly stable. When you command it to drop back down to 500, it should decay gracefully back to 500. We're using fans here because it's fairly easy to buy small DC motors that have a fan attached to them. They're cheap, and they're easy to paint. And the reason we need to paint them is that, so this cheesy drawing is supposed to be a 4-bladed fan. All right, you believe that? There's the shaft, makes it more believable. And one of these is going to be painted white, or maybe two, your choice. And as the fan goes around, you're going to be pointing an infrared emitter at the fan and an infrared sensor. And the fan is going to reflect, the white patch on the fan is going to reflect the infrared back into the sensor. So you'll be able to get a pulse out of the system every time you get a white patch going in front of the IR transistor. There's a few pitfalls with this. For instance, there's a fair amount of infrared floating around these rooms. These lights put out a little bit of infrared. But by far, the most annoying source of infrared in the room will be the photo emitter that you yourself are using. So that if you put, what you're going to have is a phototransistor staring at the fan blade out here, and you're going to have a photo emitter shining infrared out at the blade, which is then going to scatter back in various directions, get back to the transistor. And indeed, most of the light on the photo emitter comes out the front of it. That's the round part. But a little bit goes that way. So if you notice that the output of the phototransistor is always low, and we'll define that more completely in a few minutes, then you probably need to put a piece of black paper between the two. So you're going to sense the RPM, and it's not a continuous measurement, you'll notice. You only get a measurement when the white patch goes by, and then you have to time until the next white patch goes by. So you get it is a discrete measurement on every RPM, which means you get more measurements per second at higher RPM. Makes the control system a little more ugly. And so you can have the sensors running, the CPU is going to make a decision, and then it's going to put out a PWM pulse train, pulse width modulated pulse train, to the motor. Since the motor is a low-pass filter, it has a large inertia, it's spinning, it tends to... Well, how fast does the fan decay on your PC? If you turn off the power, how long does it take the fan to stop? 5 seconds? 10 seconds? So you might guess, if you just had to guess the time constant of the fan, you'd say maybe a second to drop 1 over E in speed. So you can guess that as long as the pulse width modulator is running faster than 10 or 20 hertz, that the motor will smooth the pulse width modulator out into a constant signal. So you'll get a constant speed out. So we're going to use the fan itself as the low-pass filter on the PWM. Need to be a little careful about motor drivers. I'll talk a little bit about DC motors, either this lecture or next. DC motors are ugly devices. They're inductors, and they tend to produce large voltage spikes and a lot of noise, so you have to be careful on when you drive them from a microcontroller. And we'll talk about that. And lastly, we're going to have 3 different tasks that need to be done at different rates. There's going to be a LCD update task, which of course is going to run at around 4 hertz or 5 hertz. There's going to be the motor control task, which has to run rather quickly. And then there's the very annoying human interface task, which is going to be waiting for a serial command from the user and is therefore blocking and causes everything else to stop unless you interrupt drive it. And so the serial communication is going to have to be all interrupt driven. Now, and the way we're going to do that for this lab is you are going to be required to use a multitasking kernel. Okay? You're going to be required to use a multitasking kernel, which I wrote, and therefore it must be correct. And been using it for a couple of years now. I haven't seen very many bugs. Most of the ways that it fails are because it's not set up correctly by the students or by me. But I think it's pretty stable. The nice thing about a multitasking kernel is that you can write these three tasks, LCD, control loop, user interface, as if they were separate programs, each with its own while one loop, not knowing about the details of execution of the other programs. Of course, you can't overload the CPU. There's a page which describes this. There's a lot of reading to do for this lab. The kernel, tiny real time, TRT, tiny real time. You might want to start reading up on. It has a fairly simple API. And in 3140 this year, you talked about things like multitasking, yes, and protecting memory with semaphores, locking memory, and so on. Good. That'll make my life simpler. So there's support in this kernel for locking using semaphores or mutex. There is a very primitive message passing scheme between processes. There is a real-time profiler that allows you to tell which task is running with a bandwidth of microseconds. And uses an oscilloscope for debugging. Actually, works through a small D to A converter, so you can tell which task is running. Okay, that's the high-level overview. So you're going to write a motor controller, a feedback loop, a feedback control loop, which is staring at the motor, staring at the shaft, trying to figure out how fast it's going. Make some decisions about how to control it. In this case, we're going to have to build a PID controller, proportional integral differential controller. And then uses the mathematical output of the PID controller to pulse width modulate and thereby control the speed of a motor. But where shall we start? Let's start talking about motors. Any questions, though, about the overall assignment here? Motors. Now, is there any class you take here that talks about motors anymore? What? That's not even in this department, is it? All right. It's over there someplace in MAE or something. Yeah. Okay. So let's talk a little bit about DC motors then. These are going to be small DC motors. And so the first characteristic is that more or less, if you put some voltage across a motor and you ask what the speed is, after some threshold value, they're more or less linearly related. The higher the voltage you put on it, the more speed you get out of it. The second thing is, but let's talk more about this voltage relationship across the motor. Let's say that we have some switch here, and we have some 12 volt, and we have some motor here, and we'll call the voltage across here VM. And we want to plot VM as a function of time as we open and close this switch. We're going to model electrically, we're going to model the motor as an inductor. And so we've got time this way and VM this way. Let's say we close the switch right here. VM hops rather suddenly up to about 12 volts. And if it's a motor with brushes in it, if it's commutated with brushes, you'll probably get some noise on top of this. And in fact, the noise will have a bandwidth up into the hundreds of kilohertz. It'll be RF noise. Now let's say someplace right here we open the switch. And we now have a switch which is interrupting the current flow through an inductor. And if you remember, what happens is it overshoots like that. And when you get to a high enough negative voltage that you overcome the breakdown voltage of air, you get a spark. All right, so you open the switch and you'll get a flash of light there. You'll get a spark because di dt is huge. Remember L di dt? So let's say the inductance of this thing is maybe 0.01 Henry. There's a unit we don't think of very often. So we have 0.01, and let's say the current on these little motors we're going to be using is around 100 mils. So 0.1 amp. And the switches we're going to use are fast FET switches that open in 50 nanoseconds. So the current is going to drop from 0.1 to 0 in about 50 times 10 to the minus 9 seconds or so. So you calculate out this voltage, and what do you get? Yeah, you put your hands over your eyes, is right, because this is going to be about, so a little bit greater than 10 to the 4th volts or so. So, it's a switch, it's a big mechanical switch, you pop it open, it blows a little copper off of it, you say, oh well, I could probably do that 1,000 times before the switch welds or the contacts are gone. Right, you do that with a FET switch. If this were a FET rather than a field effect transistor rather than a mechanical switch, and you put 10 to the 4th volts across it, you've got nothing. It's become gas. So we've got to do something to protect the FET switch, and for that matter, the microcontroller, from inductive spikes, and from high frequency noise. And this is more than of just theoretical interest. I've seen lots of, not lots, but several final projects fail because they were using motors and did not properly condition the motors. In one case I remember they were using it was a small ground effect quad rotor. They turn on any one motor and the system was fine. You turn on 2 motors and the CPU started to reset about once every 3 seconds. You turn on 3 motors and the CPU would reset 10 times a second. You turn on all 4 and you couldn't tell it was doing anything else. And it didn't matter which motor you turned on or off. It was additive with number of motors. And the reason was that the DC motors, the cheesy DC motors in the quad rotor, were putting out so much noise that it was affecting the power supply, and sooner or later you'd get a spike which was big enough to brown out the CPU and cause a brownout reset, which by default is turned on, by the way. And the more more motors you had running, the likelier it was that two of these spikes would overlap and get you down to the brownout threshold, which is only about 4.25 volts. So it only takes 3/4 of a volt of noise to brown out the CPU. So what do? Well, what you do always and without fail for any DC motor, if you want to have any kind of reliability, is that across the motor, you first of all put a capacitor, which remember is a very good short at high frequencies. And so it shorts out all of the RF noise. And you put a diode so that when you cut off the current and the voltage changes sign, the voltage is discharged through the diode and not through the switch. So the diode acts as a short as long as you're above 0.7 volts negative. So the capacitor gets rid of the high frequency and the junk, the spikes, during normal operation, and the diode truncates the large inductive destructive spike that would otherwise punch out the switch. But this is still not good enough. Yes? If it is a brushed motor, the way a brushed motor works is it has two contacts, which are typically carbon or carbon composite polymers, vibrating and a normal motor will make noise into the hundreds of kilohertz, and a failing motor will make megahertz noise. It's really very broadband. It sparks. It's a spark transmitter, impulse transmitter. We're going to go one step further than this, and we're going to require that you isolate the motor completely from the microcontroller. There will be no electrical contact at all between the CPU and the sensors on one side. So we'll have microcontroller, sensor on one side of a barrier, and nothing goes across that barrier except light. Okay? So we're going to use an opto-isolator to make sure that there is no connection at all between the MCU and the motor. No shared ground, no shared power supply, no shared anything. Well, it's to protect the transistor that's going to be the pass transistor. And I haven't drawn it all out yet. I mean, we need to do that next. So what we're going to do here in this lab is we're going to have you use around a 300 ohm resistor here. So this is an I/O pin. For instance, B.3, yes?
This opto-isolator system is not typically, we're just using this simply to keep ourselves from killing it.
It is often, people usually use opto-isolators to isolate low voltage systems from high voltage systems. It's a very cheap, easy sane thing to do because it'll save you hours of debugging. It completely isolates the transients away from the microcontroller. So what we're going to do here, then, we're going to use a little device called a 4N35, which includes inside of it. So the 4N35 includes inside of it a light-emitting diode and a transistor, which is optically coupled. And the isolation between them is good up to something like 1,000 volts, but I wouldn't push it. Certainly it's good at 5 and 12 volts that we're going to be using. You need the 300 or so ohm resistor here to limit current through the diode so you don't blow out the I/O pin. The output over here is going to go to oh, that's an old drawing. The output here is going to go to, well, let's just make it like a 12-volt battery here. But you will, in fact, probably use the bench power supply, the big prototype board. This will be the only time that I ask you to pull power off of those prototype boards, the bench prototype boards. You'll need about 12 volts. Motor then, so off of here there's going to be a bias resistor, call it 10K, not too critical. And then you're going to have a resistor, let me write that over here, 10K. There's going to be a resistor here to ground, and you're going to have to choose this. I can't predict what it's going to be, but it'll probably be around 1 megohm or so. Charge gets, you get photons absorbed by the base, you get charge appearing at the base because of conversion from the photons. So current flow onto the base is determined by the light beam. The light beam goes off, no more charge appears. How do you get rid of the charge that's there? It has to leak through the unbiased base emitter junction. It takes a long time to dissipate unless you have a resistor to ground here to shut off some of the current. So, the bigger you make this resistor, the more efficient this coupler is, but the lower the bandwidth. Big resistor means low bandwidth, but high sensitivity. Big resistor is low bandwidth, high sensitivity. Little resistor is high bandwidth, low sensitivity. You get to choose the trade-off. In any case, the bandwidth of this thing, the bandwidth of this opto-isolator is only about 1,000 hertz. You're going to drive this with a PWM output. PWM output. The PWM output better be slower than 1,000 hertz. This is going to go off to the gate of a N-channel power FET. Which is then going to go up to the motor proper with the aforementioned capacitor and diode across them. And this neutral, let's not even call it ground here, This neutral line in no way is connected to neutral on the microcontroller. This is a completely separate circuit. You have microcontroller over here. You have its power circuitry. No wire crosses this line. You should be able to take an ohm meter, disconnect all the power supplies, take an ohm meter, set it to the highest scale, 10 megohms, or whatever it is, 10 megohms. Put one lead on ground on this side, one lead on ground on this side, and it should read infinite. It should read overload. If it doesn't read overload, the circuit is wrong. Good thing to check before you plug it in.
What happens if that 12 volts is wrong on the breadboard?
Well, let's say you didn't bother to check it with, right. Let's say you didn't bother to check this 12 volts before you actually plugged it in, and it turns out if it's set to max, it's 22 volts. You'll burn out the motor. Let's say you plug into the negative 12 volts rather than the positive 12 volts. You'll burn out the motor. Check it. Thank you. If you hook on to ground over on the, you hook on to MCU ground and neutral over here with your digital voltmeter, put this on 10 mega ohm scale, it should read overload, OL. There should be no detectable current flow between these two grounds. There should be absolute disconnection across this optic barrier. Ah, good question. It turns out that the power supplies we use for the microcontroller have no ground connection. They are isolated power supplies. There is no connection between the output, between that coaxial power plug and power line ground. Yes, they are floating power supplies. One runs into that fairly often if you hook two boards together and you try and get, say, serial communication going between two STK500s. You hook transmit to receive and receive to transmit, and you set it all up, nothing happens until you hook up the ground wire between them, because the electrons can't get home.
Question about Opto-isolation. What the answers for the 6N137 for
6N137. Well, you know, my memory's pretty good, but I can't remember what that one does.
I'll show you after class.
Okay, this happens to be cheap. All right, the operational word for stuff we use by the hundreds is cheap.
Okay. Can we use this for RS-232 Opto-isolation then?
Barely. It's a little bit low bandwidth.
Okay.
You could. There are much higher bandwidth couplers than this. This just is cheap.
Yeah, it looks like from the data sheet the other one is 10 megabits.
Yeah, I can believe that. I mean, certainly you can get them. You can get them up into the hundreds of megabits. But this transistor here is very, very slow in these guys. The LED is fast, but the transistor is slow. So there's various ways I've seen this fail. One is you turn on the power and the diode gets too hot to touch. You say to yourself, I must have put it in backwards. Happens a lot. With the motors we're using are actually not brushed motors. They don't have brushes. They're electronically commutated DC motors. and so they are polarity sensitive. With a simple DC motor, if you hook it up backwards, it runs backwards. Right? It doesn't care, voltage, voltage. With the motors we're using, if you hook them up backwards, it burns out the integrated circuit that does the commutation, and the motor no longer turns. You throw it away. Don't do that. So that's the output side. On the input side, you're going to need to build just a little bit of circuitry. The optical emitters and the optical transistors, the optotransistors that we're going to use for the sensor, are in the same drawer because they're completely identifiable. The emitters are water clear and the transistors are black. The reason the transistors are black is that the whole plastic body of the transistor is a filter that only lets through infrared, not visible light. So you can tell them apart. What we're going to do is to bias the light-emitting diode into forward operation with maybe a 100 ohm resistor off of a plus 5 volt power supply. And then have a 2-lead phototransistor hooked up over here. So there's no base connection, just 2 leads. And the signal that comes off of here is going to be related to the light. High light hitting the base will turn on the transistor and lower the voltage. No infrared hitting the base will turn off the transistor and raise the voltage. So if you have white dots, what you'll see on the oscilloscope, let's say you have a white dot that's passing by the sensor, what you'll see is a little dip like this at regular intervals. Might be a half a volt, might be a quarter of a volt, depends on your geometry. But it won't be enough to trigger the digital input. So what we're going to do is take the output of this and feed it through a Schmitt trigger. We're going to use an op-amp for this. Op-amp comparator, but it's going to have, we can't use the internal comparator on the Mega 644 because we need some hysteresis. We need to build in hysteresis into this. So we're going to use about 20K here and about 1 meg here, but you may have to play with this value to get the hysteresis right. And then there's going to be a threshold here. Between 5 and ground. You're going to adjust this threshold so that it is just about in the middle of the time varying waveform. And when you do that, then the output from the comparator here, this output will look like a square wave. And if you use 5 volt rails for the op-amp, you must use 5 volt rail for the op-amp. If you use 5 volt rail for the op-amp, then these levels will be about 0 and 4 for the cheesy op-amps we're using. And that's good enough to trigger the CMOS input. So this can go to an I/O pin.
And another reason we cannot use the internal comparator is because if we generate a full split off of timer 0, that's B3, right? So we cannot feed B3 and B2 as we use for lab 1.
That's also true, yes. And the tiny real-time operating system uses up timer 1, so you can't use timer 1 for anything of your own. It's going to maintain all of the virtual timers and all the time bases and the scheduler for the for the operating system, for the kernel. So you're left with timer 0. Presumably you use timer 0 to do the pulse width modulation. And then somehow you have to time the rotation of the shaft, which probably means using timer 2. So in fact, you're going to run this into int 0. Int 0, what pin is int 0? I don't remember. You're going to run it into external interrupt 0, and you're going to use external interrupt 0 interrupt to read timer 2, which is going to be free running. And you say, wait a minute. Free running timer, you're reading like that? It's going to be extraordinarily inaccurate. Except this is so slow. The shaft is only rotating at like 30 a second or 50 a second. It's so slow. You have to divide timer 2 by 1024 so it doesn't overflow. And so you have 1,000 cycles to get in and out of the interrupt, and you'll be cycle accurate on the timer. So it doesn't matter. Any last minute questions on lab 3? See you tomorrow morning.